In this video, we're going to take a look at the fundamental theorem of calculus. But this video is only part one of this theorem, and specifically what we'll take a look at here is this fundamental theorem as it deals with evaluation of definite integrals. So quick recall. Recall that Riemann sums can be used to approximate the area bounded by any curve and the x-axis. So here's an example of a curve with start and end points and an area bounded underneath that curve but above the x-axis. And the idea for Riemann sums was to take common geometric shapes like rectangles or trapezoids and split that area into as many copies of those shapes as possible in order to approximate the bounded area. And so next in our buildup is a focus on what that area is. So let our vertical axis be f of x and our horizontal be x. And let's say that f of x is given in units meters per second, with x being given in units just seconds. Since area is always calculated as a product of two dimensions, this area would then represent a change in the f of x units meters per second times the x units seconds to leave an overall unit of meters. And so if we imagine f of x like this as a velocity curve, then the area under a velocity curve actually represents a change in position. But the question moving forward becomes, if Riemann sums only provide an approximation for this change, how else could we calculate a change in distance? And for that, we go back to how we would have learned this back in beginning algebra classes. We use a function that gives distance, or a position function. So in this next part, we're going to take a look at one problem setup and then two options for how to work through this problem. So our setup is, let v of t be the velocity of a car in miles per hour. And the question for this problem is, what is the change in the car's position from t equals 0 to t equals 6 hours? And option 1 for this would be to do what we discussed with Riemann sums. Evaluate the area under this v of t function from t equals 0 to t equals 6, which would be a definite integral from 0 to 6 of v of t with respect to t. Option 2, let s of t be the function that describes the position for the car at any time. If we wanted to know how far we traveled from t equals 0 to t equals 6, all we would have to do is take our position at time 6, subtract our position at time 0, our ending position minus our starting position, and we would have our overall change. And the thing to notice about these two options is if the integral on the left and the difference on the right, if they calculate the same thing, then these two expressions must be equivalent. And additionally, and this is what leads us into the big takeaway from this video, recall that the derivative with respect to time of position is velocity, which must mean that the integral or antiderivative of velocity is position. So in one calculation, we integrated velocity from 0 to 6, and the other, we evaluated the change using its antiderivative. And this leads us to the fundamental theorem of calculus. And as mentioned before, this is the first part where we're going to deal with evaluation. Given a function f of x, so that Criteria 1, f of x is continuous on a closed interval a to b, and criteria 2, f of x has antiderivative capital F of x, the definite integral from a to b of f of x with respect to x is equal to big F of b minus big F of a. Or to summarize, the area under a curve on a closed interval a to b equals the antiderivative for that curve at b minus the antiderivative for that curve at a, which is a major connection. If we can simply reverse the differentiation process, we can calculate exact areas under any curve just by doing evaluations on that antiderivative. So let's work through the following example. Let's calculate the integral from 1 to 4 for the function 2x minus 3 with respect to x. What the fundamental theorem says is, first, decide if f of x is continuous on the closed interval provided. This is a linear function, so it's always continuous, so we've passed that first criteria. Step 2, evaluate the antiderivative for this function. In this case, the antiderivative of 2x minus 3 is x squared minus 3x. Don't forget to include a plus c. There could have been some constant there. And since we've done the antiderivative, the integral notation is not needed anymore. So we note that we are still working on the interval 1 to 4 with this vertical bar at the end. And now step 2 is done. Step 3, the fundamental theorem says that we will evaluate the area for the original problem by evaluating this antiderivative function at our end boundary, in this case 4, minus the function at our starting boundary, in this case 1. Quick thing to note, if you're going to have a plus c minus the same plus c, then the plus c is not needed when using the fundamental theorem to evaluate definite integrals. Simplifying the rest, we'll get 16 minus 12 minus the quantity 1 minus 3, which will give us an overall area of 6. The definite integral from 1 to 4 for the function 2x minus 3 with respect to x is exactly equal to 6. So not only much quicker than Riemann sums, it doesn't provide an approximation, it provides an exact value, which we would always prefer to use. And so we'll finish with one more example. Evaluate the integral from pi over 3 to pi over 2 for cosine of x with respect to x. Cosine is an everywhere continuous function, so we'll move into finding its antiderivative, which is sine of x. And we'll evaluate that from pi over 3 to pi over 2. The fundamental theorem says this will be equal to sine at the end boundary, pi over 2, minus sine at the starting boundary, pi over 3. Sine of pi over 2 is equal to 1. Sine of pi over 3 is equal to square root of 3 over 2, and there is our final result. We can simplify this back to 2 minus square root of 3 all over 2, and there is the number that represents the exact area under cosine between the boundaries pi over 3 and pi over 2. And that will do it for part 1 for this lesson on the fundamental theorem of calculus. Thank you for watching.